Hello, everyone, and welcome to another interesting episode of the Geek Narrator podcast. Today, I have Lintao with me, who is the CEO and co founder of EloqData. And EloqData is this platform that is a core innovation in itself when it comes to databases. It has a support for multimodal data, it has support for high scalability, high performance, super elastic cloud offering, asset properties. So I'm just naming all the important things when it comes to databases, and it's there in EloqData, right? So today we are going to talk about how it all works, what is the core innovation behind EloqData, and just try to understand overall design, architecture, some of the choices they have made, some trade-offs, maybe some challenges, so we can all learn together. So welcome, Lintao. I'm really excited to have you today.
Yeah, thanks
with
a lot
this,
for the invitation.
absolutely.
Sorry.
It's a pleasure. I would love for you to start with a little bit of introduction so people know who you are, what you have been working on, and a bit about EloqData.
Yeah, thanks a lot again. So it's a great pleasure to be here. I was a big fan of the program. My name is Lintao, and I started the EloqData in 2021. So it's actually been quite a few years. And we just start get out of the stealth mode and announce our products. So I'm really glad to have this opportunity to introduce some of the ideas, some of the thoughts we have during this process. The company was, as I mentioned, was started in 2021. At that time, we found that there is a very messy landscape of databases out there. You have a very large number of choices when you build your data infrastructure. And at that time, we foresaw that going forward, this is unsustainable. So used to be people were talking about one size does not fit all. Now you basically have millions of choices, and each of them holding a very small piece of your entire data. And what can we do? How can we change this situation? That's how we actually started EloqData, this company. So as you have already mentioned, that what we are actually building is a very new database architecture. It's a new way to build databases. So the idea was we want to abstract away some of the common parts and put them into a same place. This is the core innovation for the company. And the piece is called data substrate. So data substrate is this thing that is common to all the databases. You need to handle, for example, cache scalability, like fault tolerance, elasticity, storage durability, ACID, all those kind of common things. And on top of that, we have different kind of compute engines. And on bottom of this, different kind of storage engines. So compute engines essentially try to interpret what kind of data you're trying to process and what kind of query, how would I run these queries? And the storage basically means where do you want to put your data, store at different medium or in different clouds. So by decoupling all these things, we can assemble a database with all the nice properties provided by the substrate, but not constrained by all the environment and the computation need. So that's how we actually do this new computer architecture. Yeah, I think this is a new way to rethinking about the database. So by doing so, we can actually simplify the database needs for all the companies out there. And we can use different compute engines to handle different kind of data models. And we combine them all into the same kind of data substrate so that we can aggregate all data without wasting any of your storage or computation or a different kind of resources.
Makes sense. And I'm already very excited to learn more about how it all works. You mentioned a couple of things. You mentioned about abstraction. You mentioned about decoupling compute and storage. You mentioned about a component or a system called data substrate. So just to make sure I understand correctly, what exactly is data substrate? Is it like an aggregation engine that behind the scenes abstract away a lot of the complexity around compute, around data modeling, caching, fault tolerance? Is it like a layer that hides all the complexity and make it work for you?
Yes, that's right. So basically, data substrate is basically the common piece. So when we are trying to build a database, everyone knows that from the textbook, we need to build like query optimizer, query engine, buffer management, write-ahead log, and then the storage engine B-tree or something like that. So usually even though when the textbook describes this as a layered kind of architecture, in practice, what people are doing is you build the entire thing as a monolithic database. So we have a lot of examples out there old ones like MySQL and the PostgreSQL, and even the new ones, we start to try to separate some way. But still, for example, PingCap, TiDB, or CockroachDB, they try to separate the storage from the compute part, right? But even though the architecture was originally designed like this, it's actually very hard to reuse some of these components. So that's why we thought about this architecture and try to extract the common piece, which we call a data substrate. So the data substrate essentially handles the common part, which is actually in our case, from the technology point of view, is essentially the buffer management and the write-ahead log. So it's essentially part of the state. How this state is going to be manipulated and how are they going to be maintained, kept with their integrity, consistency, those things actually are common for all the databases. All the database needs at least a desired ACID property or scalability. But previously, because of the issues like performance issues and also bad abstraction, it's usually very difficult to decouple that part from the compute engine or the storage. For example, in many of the databases, storage, for example, is organized as a page. And then in the buffer management part, we also organize it as a page. And even at the compute engine part, we sometimes assume that data are organized as in pages. So that's actually a kind of a break of abstraction. And this makes it very hard. If some of the databases, computational models doesn't want a page abstraction, it would be very difficult to adapt. Or of course you can, but usually you will lost a lot of your performance. That's really the key innovation in our data substrate abstraction. So what we are trying to do is keep the interface as minimal as possible with fewer assumptions as possible without losing the performance benefit. For example, you can always treat everything as a key value, right? That's very simple, right? Everything can be explained, can be implemented as a key value. But then the question is whether that is the best, whether it will lose performance. And every time when you do a copy or when you do a filtering, you need to pull all the data, the key value data back and then filtering out, whether that's the best thing or not. So that's actually the thinking we have. And what we are actually able to achieve is by abstracting out all these complexities and keep only the necessary interface, we can make it both high performance as well as modular, which is actually a very difficult, hard trade-off or we can avoid.
Okay, I think there are really important and interesting points that you mentioned, and I would love to go deeper into each of these. But I think at the core of the design, I think what is the highlight is decoupling, right? And at the outermost layer, which is the API, keeping it really simple. So with decoupling at each layer and not leaking the abstraction details from the lower level, let's say the storage to compute and then compute to API layer, I think a lot of complexity is also reduced, as you mentioned. And you're able to reuse the common parts, as in buffer management, wall, consistency, probably some parts of fault tolerance. If I understand correctly, a lot of these, like other databases, are also trying to achieve some sort of decoupling. When it comes to, let's say, having a Postgres compatible API layer, then there is a compute separation, then probably Postgres layer or on storage side, or even in some cases, object storage and so on. Talking about the high level differences, what is the core innovation apart from decoupling each of these resources? What is the core innovation in your view?
Yeah, I think there are actually mainly two core innovations. I think the first is basically as I mentioned, the abstraction part. So the abstraction part is actually pretty tricky. So previously, if you think about it, previously people have been doing this for a long time. It's not we are the first to think about we need to abstract, right? But the traditional way of doing this always suffer a lot in the performance side. And that's why usually when people are building an engine, they still start from scratch. Though we are now seeing more and more modularization in the AP part, like now our AP engines we are trying to do a lot of this modularization and common pieces, right? So but on the OLTP side, it's still very tricky because we are actually managing memories. So you need very low latency. And whenever you introduce some abstraction that is not optimal, it will introduce unbearable performance overhead. So that's why it's still a very challenging piece of doing this abstraction. So the API part, I would say, is one of the main innovations. The second one is actually on how we actually implement these things. So for example, in our architecture, we call it a shared everything architecture. So previously we have like single node architecture. Then we have shared nothing architecture, right? So then recently, I think in the OLTP case, we have Aurora or those architecture, they call it maybe shared storage architecture, log shipping. So the reason we don't have a shared everything architecture is exactly because of the things I mentioned. It's very difficult to make everything efficient. In our case, we actually implemented a lot of innovations in this front. So some of them are actually implementation related. For example, like we use a core per thread kind of model. And sometimes some actually algorithmic innovations, like how can we do distributed transactions in a scalable way when they are either in a single node or when we are performing that in a cluster. So by doing this, by all these innovations, we can now achieve that a database, this architecture can scale from either a single node, even a single core, upwards towards a large distributed system. And in our mind, a data center is essentially a large computer. So that's why we call it shared everything, right? It's just a computer. So what's the difference? Is some of the communications needs to be cross node. Some of the communications, if everything is collapsed into a single node, then it must happen in a single node. They may use different kind of message parsing, different kind of communication method. But overall, so from each shard, that's what we call it. It's the abstraction of running the kind of execution model. From each shard's point of view, it's essentially the same. You need some data, you get some data from another shard, which could be in the same machine. You do message parsing using shared queue or something. And if you want to grab a data from externally, then you need to do a RPC call or something. But that's only the physical part. The physics have to limit your doing that. But from the shard point of view, I don't care. So then it's the policy, right? So if you can collapse everything into a same node, then of course your performance will be about the same as a single node. Now the difficult part about treating a data center as a large computer is when we have a large computer, it will not fail, or it will not partially fail. Everything will fail together, or they won't fail at all. So the tricky part is in a distributed sense, you actually have to treat about a failure case. So that's why you need to handle, if one of the shard fails, what are you going to do? You need to detect that and you need to recover from that. And that's actually pretty tricky because that's actually the traditional difficulty of a distributed database, right? How can you handle that? That's also some of the innovations we have. Yeah.
Okay, that's very interesting. And I think it's the right time. Probably we take an example, right? And try to go deeper into how it all works, what components are involved, and understand what happens when there are failures, how our asset guarantee is maintained, how is performance maintained, and so on. The easiest example and the most common example when it comes to transaction is about any financial transaction, right? It's like a financial company, and I want to use EloqData, right? Let's say I've been using a legacy system, OLTP system, and it's creating problems. And I want to now, let's say, move over to EloqData. How would you guide me moving the workloads to EloqData? What will change from the API perspective? How will the ingestion happen? So let's start from the ingestion. How would that work?
Yeah, that's a very good question. Of course, we are a technology company, but we are, of course, not selling technologies. We are actually selling products. So that's actually a good question about what kind of products we are actually offering. So what we are actually did is we built this very key innovation data substrate architecture in the last 4 years, actually. And what we did is added some of the compute engines and the storage engines on top of the data substrate and below the data substrate. So now we actually support different kind of APIs. So from our point of view, API is essentially how you access your data, right? We actually, because our architecture is modular, we can actually plug in different kind of compute engines. So currently we have 4 compute engines in our product portfolio. So we actually support Redis API, we call it EloqKV. We support SQL API, MySQL API, we call it EloqSQL. And we have MongoDB API, we call it EloqDoc. So of course, you know that these are very popular databases and pretty much all the internet is built on top of these APIs. What we did is try to leverage some of these code and also some of the implementations because a lot of these projects are open source and we don't need to reinvent the wheel. we can just borrow some of course, observing the licenses and everything. We borrow some of the code base. And then we assemble this with our data substrate. So the idea was traditionally, it's hard to do because of the abstraction part, right? It's almost impossible to support, for example, like MySQL on top of PostgreSQL. But in our case, it's actually not only doable, and we can actually do it pretty efficiently. Of course, there are some work needed, but not that much. So it's several months of work instead of several years of work. And after we did this, we have these three, EloqKV, EloqSQL, and EloqDoc. And also, we are now also building a Converged database. So the Converged database means I can combine all these different data modalities into a same database. So what's the benefit of that? The idea was if you have a single database that can handle different data models, then what you can do is you can save a lot of things. You can simplify your management and so on and so forth. But another very important thing is that you can actually perform transaction across these data models, which is traditionally very different to do. And that's actually something from the start, what we actually observed. So when we started the company, we look at the landscape, right? So if you need to build a data pipeline, if you want to support your business, you need 5, 10 databases trying to do all different kind of things. The main issue is how would data flow between them and what happens if something fails. And this is a very tricky problem. It involves a lot of manual work. If all the data can be managed in a single database and we can have transactions between them, we can either ingestion all fails or succeed. That would simplify a lot of the operations. This is especially true in the AI age, which we can talk about later. But basically, that's actually the product we offer. We offer either the industry standard APIs, or we have a converged database, which combines all these APIs. Even though from the users' point of view, they are still, look at it, it's just a Redis. It has all the Redis APIs. It has all the MySQL APIs. It has all the Mongo APIs. But it actually benefits from all the advantage from the data substrate. For example, Redis traditionally was a in-memory cache, right? So usually the data got lost if you don't shut down properly. But in our case, we are actually, EloqKV is a real database with write-ahead logging, with all the checkpoint and everything. So it can support consistency. It can support different kind of isolation levels, read committed, read serializable, and so on and so forth. We can actually support distributed transactions. So we can actually support cross multiple nodes. You can do an atomic get or put, and you can support session-based transactions. You can start a transaction, do something, and then either commit or abort. Similarly, like MySQL is a single node database. Traditionally, if you want to build a distributed MySQL, you have to leverage other tools, like, for example, CockroachDB or TidyB. I think TidyB is MySQL compatible. But in our case, but TidyB, you have to essentially replace everything, right? TidyB, the entire stack is a different stack. In our case, our front end, everything is a MySQL, but we use the data substrate to provide the scalability, the fault tolerance, the replication, all those kinds of things. Similarly for Mongo. And so that's actually what we can achieve with data substrate. And now for people to migrate, it's actually very easy because all the standard tools work. So if you know how to migrate MySQL, you know how to migrate to EloqData. So beyond that, we also support different types of storage. So one of the key advantages, we can also swap out storage engines. Now what we can do, the main offering we have is using S3 as the main storage, persistent storage. Of course, you can use local storage, you can use RocksDB, for example, but that won't give you the reliability or the fault tolerance. It's a single node solution, right? Well, we can support that, but we also support different kind of backend. One of the key advantages, we can use S3 as the main storage engine. The reason was because we actually separate logging and storage and cache management, buffer management into separate pieces. What we are actually doing is we use, for example, cloud like a EBS, like a elastic block storage as a logging device, so that we can make sure that we have enough I/O, or at least enough write capacity to keep your write-ahead log. And then we can use NVMe local storage to hold your data to be able to read. Of course, NVMe local disk in the cloud is ephemeral, right? So if it crashes, the data will lost. So now what we can do is when we do checkpointing, when we save data to the store, we use S3 as the storage. So in that case, we basically won't lose data because EBS is reliable. S3 is durable, not reliable, but durable. Essentially, NVMe is not supposed to be local SSD, is supposed to be ephemeral. Traditionally, people have been trying to do this. In the OLAP case, it's actually relatively easy, but in the OLTP case, it's actually very challenging. A few companies have been trying to do this in the last, I think, a year or two. People have been, and you have a few interviews on some of the folks doing this. But it's a challenging thing. And how can you maintain the performance? In our case, it's actually pretty natural, very natural, and we can do it very quickly. So another feature is, for example, because we can swap the storage engine, we can do checkpointing and branching capabilities, which was introduced by NeonDB a while ago. But in our case, it's also a few months work. It's very simple to implement. That's how the decoupling kind of biased. Yeah.
Makes sense. And that is really powerful. Just to validate my understanding, are you saying as a financial institution, let's say I have a huge MySQL cluster, let's say a sharded MySQL cluster. I have a Redis cluster where I want my key value storage. Let's say I also have some MongoDB use cases. Are you saying that I can get rid of all these components, use EloqData, and basically simplify my architecture?
Yes, that's the goal. Of course, I think we are still trying to get into the product market fit, and we need to basically convince everyone this is a valid architecture. We are still a startup company. I'm not so have the hubris to say that we are going to dominate. That's not the case. But I think it's providing some thoughts or the value. What we feel our value is, we want to shake the database landscape to see there are some ways, that there are some better ways. Let's try to do it in a better way. So that's what we hope we can achieve.
Makes sense. I think it's a great vision to have, because a lot of applications, at least I have faced in my career, is they deal with a lot of complexity. And it's not for like unnecessary complexity. There are valid reasons that they have to support multiple databases. They need to have a cache. They need to have some fault tolerance. They also need to have multi-region deployments and so on. But the problem is, it's a hard problem, right? And it takes away a lot of energy from product engineers to be focusing on what they actually want to build. So I think it's a powerful idea. And I want to understand how does it all work? So let's say I have MySQL, I have my Redis, and I have my MongoDB. When I start migrating my data, how does it all work? How does the data substrate layer know what kind of data storage I need to use? How does the ingestion happen? And with that, I also want to understand the very important feature that you mentioned, that you can run transactions across multi-model data that you have, which is a big pain when you have to do it yourself. So how does that come into picture? Let's throw some light on that.
So from the user's point of view, so we actually currently, our implementation is not reinvent the wheel, in the sense that we try to keep it as compatible as possible. So from the user's point of view, it's just a MySQL database. You use one port to ingest the MySQL data. You use another port to ingest the Redis data, for example. Redis, you don't need to ingest, but whatever. And you use another port to access Mongo. So from the user's point of view, it's just 3 different databases. But these databases, underlying them, they have the same data substrate. So they will basically, all the data will be managed by the same buffer pool, by the same storage engine, and by the same write-ahead log. And so that's why you can actually achieve transactions across them. Of course, we need to modify the transaction semantics, modify the API a little bit. In this case, because we have to, usually what you do is you start a transaction, and then you do all these things, and then you commit or whatever. So the commit part and the start part need to be matched. You have to have a common transaction ID or some kind of communication. But that's the only minor thing you have to deal with, the complexity. But it's actually much, much simpler than inventing a new programming language or API that can handle different types of data. Because we can certainly try to build a multimodal query language. That would be, first of all, it's going to be a huge effort. Secondly, it's not standard. Everyone have different opinions about which one you should use. Your things it sucks. So we, as a startup company, we can't. It's very hard for us to educate the public So what we choose to do is first to stick with the existing API as much as possible. So users have a very minor migration pain. But of course, in the future, the key innovation in our case is the underlying part, right? So in the future, we can build other types of compute engine, which may support cross data model transactions, may support different kind of data models in the same language. You can do query optimizations both on, for example, a graph and a SQL table, which I'm not sure is still an open problem, right? But I think these things can be built on top of this architecture.
Yeah, I think that's a very important point. And I would avoid any migration where there's a huge learning curve, right? And if my API stays the same, I have to do minimal changes to my code, and which is a win because then I can move it easily. I don't have to change my code a lot, write tests, do some migration, probably have some incidents and so on. So I think if that pain is gone, and as you mentioned, you don't want to reinvent the wheel. You want to use existing standards, and these standards are battle tested. These standards are used by everyone. So why not? And it's a powerful idea. Talking specifically about the MySQL use case, let's say I have like multiple shards of my MySQL database, and then I need to move my data to EloqData. The migration itself is fine. But talking about the abstraction, when I am dealing with multiple shards, this abstraction is known to my application that I have multiple shards, right? When I move to EloqData, I'm not sure how the mapping between my MySQL shard and EloqData happens. But in a way, from the application's perspective, it moves from a physical abstraction of having multiple shards to more a logical abstraction. So how does that transition happen?
Yeah. So that's also another very good question. So I think sharding or manual sharding, I would say, is actually an artifact caused by traditionally non-scalable solutions. So previously, not only MySQL, but also, for example, Redis, they also have the concept of sharding. You have a very large data set. You usually want to have some sharding, some way to shard the data. And sometimes because of the sharding, your client also need to change a little bit, right? So because you need to know where the data is and your client needs to direct your query to that particular shard. That's actually the pain. We feel that it's unnecessary. Of course, we can always add hints, right? Those are the policy part. But from the mechanism part, you shouldn't do that. From the user's point of view, you shouldn't worry about that. Of course, we can do performance tuning, so we add all kinds of hints. By default, you shouldn't do this, shouldn't be forced to do this. So that's what we have. We actually have a very client transparent way to doing this. So from the outside, you look at the MySQL, it's just there are a lot of ports. Each of the ports, of course, is just a MySQL. You can regard them as the same MySQL instance. Everything will happen just as a single database. You put a lot of data in there, which could, of course, be more than one node can handle, but that's fine. The backend take care of that. It will automatically do the sharding, not manual sharding, but automatic sharding. And it will automatically put data in the right places and trying to direct your query to the right places. And the performance usually is very good. It's quite good. And of course, there is always the physics you can't avoid when the data is residing in one node. If you want to pull that data, that's a policy part, which we can fix using some configuration, force the data to be collocated or something, but that's not necessary.
Okay, so that makes sense.
Yeah, this is actually one of the key advantage, I think, from the traditional architecture and the new architecture. Essentially, what we're trying to do is trying to avoid complexity as much as possible from the user's perspective. But we actually have a lot of complexity, of course, in the backend. Essentially, we try to remove the things. Users shouldn't, a good infrastructure, from my point of view, is something that the user shouldn't worry about anything. You just use it and it should work. Of course, the performance tuning engineers will go into there. There are always millions of knobs you can tune. But from the user's point of view, you shouldn't be reminded, the data is sharded. You can't join this table with that table because something that is too large is out of memory. Physics we can't overcome. There's no way we can put more data in a single node over the memory, but we can at least try our best from the mechanism point of view. Yeah.
Yes, I totally agree. A lot of times I've seen these infra-level details when they get leaked into the application level. There are two things. One, it's really brittle for your application to break because as soon as something on the infra changes, your application needs to change, otherwise it doesn't work anymore. Second, the overall complexity of the code is exponentially growing because infra is changing, there are tons of failure modes at the infra level that you have to worry about, and so on. So yeah, more power to you when it comes to making things simpler for users, and I totally appreciate the idea.
Yeah, let me add another thing is, I think one of the thing we actually also feel is very importantly to us is we feel that previously we break the database into multiple pieces, like for caching, it's for performance. You want to cache the hot data, right? And then you put the real data into MySQL or something. So those are actually also another kind of complex. It's also a trade-off people used to make. The reason was because MySQL was not fast enough, right? So you have to cache into Redis. And Redis is not persistent, so you have to write to MySQL, which causes a lot of complexity. And this is, for example, all the data, you have to have two access paths. If something fails, you go to, if it's cache miss, you go there. And then you have to maintain the cache consistency and everything. That's actually another thing we feel that it's something, the trade-off was because of the infrastructure. And if you have an ideal infrastructure, let's imagine what the world would be, right? So if you have an ideal that doesn't have these trade-offs, you generally won't do this kind of multi-tiered, multiple data things, right? So how can you achieve that? That's basically the question we started to answer. We try to answer from the start. So for example, in our case, Redis is actually we can achieve Redis kind of performance in EloqData. So what we can support is over a million read-write queries per second on a single node. And of course, Redis is generally simple. It's very easy to scale, so you can scale out and scale up. We can not only scale out, but also can scale up because Redis traditionally was a single-threaded implementation, so you can't scale up. You can't add more cores to exact performance to get better. Nowadays, there are some work, including the Valkey people and also the Redis people are also trying to do some of the offloading. And the Dragonfly DB is another example trying to do multi-threading. But anyway, I digressed a little bit. But basically, so this Redis and it's actually a pretty good API, right? A lot of people like the Redis API. But the reason they don't store data in Redis is because of the non-persistent, non-transactional, all those trade-offs. And in our case, the EloqData supports all these transactions while still maintain the same level of performance. This is actually very powerful because, for example, one of our clients was using JuiceFS. JuiceFS is a file system using S3 as a backend. And they have to keep the metadata like file directories and the file metadata in some places, right? One of the better choice would be using Redis. The problem is that Redis is not durable. If you lost your metadata, you're gonna suffer. Also, Redis is not scalable. You can't add a lot of chunks because then you won't have the consistency. Redis can do single node transaction, atomic transactions, but it can't do this in a cross node manner because sometimes when you're trying to move a directory from you move a file from one directory to another, you have to do this atomic operations. That's necessary. But if you can't do that in an atomic way, there could have file or metadata corruption, file system corruption, which is pretty bad. So that's actually one of the pain points. And if you just use our system, it automatically handle all those things for you. So that's actually the nice thing about using a unified structure. And now the question is whether your API, whether you really need the MySQL API to do queries, for example. If you are just doing move from one account to another or whatever, you may not need the complicated query optimizer or whatever, right? So that's how we see this world in the sense that you should use the tool for your kind of workload without worrying about the underlying capabilities of the underlying infrastructure. And by doing this, we also simplify the infrastructure deployment. And one of the very frequent failure pattern is cascading failure. When you have a cache layer, if one or two of the node fails, even though you may lose 10% of your cache layer, but you may increase your backend workload by like 5x, 10x, because mostly the data is supposed to be cached, but then suddenly it's not. Then it all hit the backend, then you have a disaster. You have to over-provision your backend a lot. And this thing shouldn't happen. If you lose 10% of your data, your node, computational node, your resource, you should lose maybe 10% of the capacity. That's the ideal case. Right? So that's what we are actually trying to achieve. Of course, you can't lose data, but the computational resources, memory, if you lose to 10%, it shouldn't cost that much have a flag.
Yep, interesting. I have one question though, and maybe this is just my lack of understanding. But so let's say I have MySQL, I have Redis, and you mentioned, and there is a lot of first principles thinking there, right? Because why do I need a cache? Because MySQL is slow. And why do I need MySQL? Because my cache is not persistent. When I talk to EloqData, right? Why do I need to know about caching when I can just talk to EloqData and assume that there will be a cache? Can we also abstract that, or is it already done?
So for example, in the Alloc KV part, so you can actually do that. So you don't need to worry about caching itself, because if you configure your Alloc KV, which is a Redis API, right? And you make it persistent, and we can enable that, just to turn on a flag. By the way, we'll also support non-persistent mode, because if you want persistency, of course you need to pay something. You need to pay the write-ahead log. And so the write performance will suffer a little bit. But you may also, if we do the checkpointing, sometimes the data may not be in memory, so you will pay the load from the storage. But if you can, so basically we have flags to turn this on and off. If you turn them off, that means you are really making it a real database. And then when you do the read, you actually get the performance about the same. So pretty much the same in our case as the read from a cache. So we can, so the write performance may be 100,000 or 200,000 QPS, which is actually quite nice already. And the read performance can still be 1 million. So 1 million QPS on a single node, which is huge, which is actually much better than Redis, even when Redis operates in a cache mode. So that's really exactly the idea. You don't need to regard this as a cache. It's just a database. Every time you query, you got the up-to-date data. Of course, in the MySQL case, it's a little bit tricky, because in the MySQL case, because of the query, right? So that's one of the things. We are not changing the API. So you have one query could affect another query, right? We don't know, at least in the MySQL, in a SQL language, you don't know which query will affect the other one. So you don't know what data is being modified. Of course, there's a lot of research out there trying to do this, trying to make sure that if you use the same query, SQL query, and then if the underlying data didn't change, then you will get the cached result. But that's generally a hard problem, because you don't know, you can't monitor which data will affect your query. For single queries, KV, that's definitely doable. Yeah.
Okay, yeah, that's fair enough. And I'm also curious about transactional behavior that you mentioned across these type of different data storage things that you have. Let's say when I make an update to my MySQL table, I also want to update my Redis cache or my document database, and I want to do that transactionally. So if I have different systems where these transactions are not possible, I have to pull that logic up onto the application, and that complicates my logic. But now that EloqData provides this transactional behavior, how does that API change? How do I think about that from an API or a user perspective?
Yeah. So currently, by the way, the Converge DB is still a work in progress. So we already released the SQL, the KV, and the doc. Yeah, and you can actually already try it. But the Converge DB, we are still working on it. It's probably going to be another couple of months. By the way, the other databases are out there, not only available for your testing, but it's an open source project. So you can actually download code and try to examine what's going on internally. And we also have cloud native support, serverless support. So you can just sign on with an account, just to try to use them. The Converge DB, it's still a work in progress. But what we are trying to do is essentially get the transaction ID, trying to communicate a common transaction ID to the user. So the user when it needs to start a cross-data model transaction, it needs to get a context, essentially. You need to know what the transaction context is, using a handle or ID or whatever you call it. And then all the follow-up operations can be done just with that context. After you do this, the database knows that these operations will belong to the same query, so that they either need to be succeeded or failed at the same time. And then when you commit that context, commit that transaction ID, it will basically know exactly what to do. So this is essentially the same as other kind of transactions. In SQL, it's the same, even though the context is hidden, right? So you start a transaction, which essentially you take that handle. And then you do a lot of these instruction SQL sentences. each of the sentence you can think of, it's just a query into the database to interact with the storage engine. And all these things are exactly the same will be happening in the data substrate.
Okay, that is interesting. I want to go a bit deeper onto the, let's say, the traditional MySQL use case. I move my MySQL workload to EloqData and I use the same APIs. Comparing the performance of MySQL cluster that I have and EloqData, what is the difference in EloqData that it gets better performance? And with this, I also want to ask, what happens, let's say, when I insert a row in my SQL database in EloqData? What are the phases my data moves through and what exactly happens?
Okay, so this is a very good question. So this essentially touch the core of data substrate, how data substrate actually handles data. As I mentioned, in Eloq data substrate architecture, we really treat the entire data center as a single computer. So essentially what your data, your query goes through the life cycle is almost exactly as traditional database, what it will do. For example, we are actually using Eloq, we use this data substrate as the buffer manager and also the write-ahead log manager, right? So what you will do, your query will go through is a query goes through the query parser or query optimizer and then basically be translated into the operations, get, set, or filtering, whatever, into the data substrate fabric. And then that will basically one of the shard, we call it the transaction managers, basically a TX manager, that will basically handle those operations and it will create a transaction context and then try to execute all those operations one by one. So and this is exactly as the same as what the traditional database, single node traditional database is doing. It will try to acquire logs and then modify in-memory data, maybe have a local copy of the data. After you do the transaction, when you commit, you want to write them back, install all the modifications. So before you install the modifications, of course, you need to write a head log to make sure that your data is persistent before you do the in-memory modification. So if this transaction node fails at that time, it will basically be recovered in the there will be another mechanism to detect whether that transaction manager is still alive or something. So that's essentially exactly the same as a traditional single node database. Of course, the difficulty is in the details. So for example, one thing is if you are doing a distributed transaction, how would you write to the write-ahead log? Because we would have multiple write-ahead logs. And that's one of the things. So in our case, we actually have some way to how to order the log entries. And we use a distributed virtual log-based clock scheme. So we try to avoid the central timestamp oracle, so that our stuff can scale. Another thing is that if of course, as I mentioned, you need to acquire logs and so on. So if you acquire log from another node, right? So that log may got lost because that node could crash. And then if you acquire a log, you try to modify and they try to install. In between, the node failed. What are you going to do? So there will be another set of algorithms trying to detect whether that thing failed or not. If it fails, how can you recover? Or you release all the orphan logs, because the TX manager could also fail. It can hold a log for infinite amount of time, then it failed. And nobody is going to release the log, right? So you want to have all these kind of coordinations to deal with a failure case. That's what I mentioned previously about part of your system. Even though I treat it as a single computer, but part of the system, you can see that the thread can die at any time without any reason and not causing the entire program to fail. How would you handle that? So that's what we are actually performing. So there are a lot of details, a lot of intricate things on this, and we are actually writing a paper trying to submit. So I'm not able to discuss this in too much detail because it's very technical. Traditionally, what people are trying to handle this kind of failures is using so-called two-phase commit. So that makes everything very different from a single node. That's why distributed transaction is always considered to be difficult, because of course it can be done, but it's expensive. That's why all the distributed transaction is hard to do. So people can't scale their MySQL database, for example. So traditionally there is a trade-off, right? So we have the performance, we have the scalability, and then we also have the transaction ACID guarantee. And in the last 20 years, of course, before 2000, it's just people choose performance and single node. They can't do scalability. And then in the last 20 years, because of the explosion of data, people have to have scalability. And there are a lot of trade-offs made. So originally, what we are doing is NoSQL, right? Since you can't keep the transaction semantic, so you just throw away the transaction semantic. And that's you choose performance and also the scalability. But after a while, people found that this is very hard to use. Without the transaction guarantee, a database is really hard to use. So now people found that, okay, I need transactions. So what shall I do? I implement a transaction. So that's started from Spanner. Google did this very influential work. And then a lot of open source, CockroachDB, Yugabytes, as I mentioned, PingCaps, IDB, they tried to use the Spanner architecture, separate the storage and the compute layer using a key value as a storage layer. And that is essentially what we choose is scalability and also the guarantee. But then it suffers on the performance side. So generally, even if you collapse all the node into a single node, collapse the deployment into a single node, it still performs much better, much worse than traditional single node database. So that's how in the last 5-10 years, shared storage kind of architecture becomes popular. And what Aurora was doing on NeonDB or EloqDB, SQL Server hyperscale, what they were doing is I have a single node with write capability, a single writer. And then the storage can scale, but still I don't need to maintain distributed states. So that's essentially what people have. At this moment, at least before EloqData, you have to choose among all these three, which makes things really complicated. That's what we are actually, EloqData can solve.
Interesting. And I'm looking forward to the paper, by the way, to understand a bit more technical details. I understand that you cannot share right now, but these are really interesting details. And thanks for sharing the different paradigms people have been solving for and why it creates a problem and so on. And I can imagine all these problems because I've used some of these systems. And yeah, there are issues at high scale, and especially when there are failures happening. Interesting. You mentioned thread per core architecture, right? Let's talk a bit more about that, understanding what benefits you get out of it and what made you choose that.
Yes, this is also a very, very important question. Traditionally, when people were designing, a lot of the architectures or the database designs was like 40, 50 years ago, right? So the key architecture design decisions was based on the hardware available at that time. Traditionally, the I/O is usually very slow. You don't really care that much because CPU is fast. You don't really care that much about wasting CPU cycles. You really care about how to get your data I/O as fast as possible. And that's how traditional databases was designed. But in the last 5-10 years, we already see that the I/O is becoming faster and faster. It's very easy to scale the bandwidth. It's not necessarily easy to scale the latency, but at least from the bandwidth point of view, you can scale a lot. And on the latency side, NVMe, SSDs, and also the RDMA networking is also hugely improved on the latency part. So nowadays, you can actually get I/O in the hundreds of gigabytes per second kind of range. That's very fast for a very large node, right? So all the bottleneck is actually on the CPU. So what we are trying to do is trying to maximize the usage of CPU as much as possible. That's why we actually designed the entire system as a thread per core architecture. The thread per core, if people are not familiar, is essentially using something like a user space threading. You can think of that like that. Essentially, each thread will not be yielded. It will not be handled by the I/O, the operating system. It's just trying to do as much work as possible. If there's any work in the queue, it will just try to get data from the queue. But what about I/O? For the I/O, you actually have to do asynchronous. Essentially, you have to put a request out there and then put the completion into a queue. And when the data is available, the thread will just pull that data out of the queue and try to do the work. By doing this, the I/O is handled asynchronously offline, not offline, but it's not in the same thread context. That way, the thread can keep busy doing whatever the work is available for it to do and trying to accomplish as much as possible without stalling, without yielding to the rest. That's really important because by doing this, we really achieve the maximum the CPU usage. So by doing this also, we can treat each of the thread as a kind of a unit. Essentially, thread is, which we basically call it a shard. Not exactly the same, but we try to treat this as similar. So each thread, when it talks with another thread, it's still going through that queue, because you can't just, traditional way is you just wait there and block, right? So you ask for data, the other thread will try to do something and signal you this thread, which is going to be expensive because we don't want to have the OS get involved. So now everything is going to through message parsing. And by doing this, we avoid that wait part, avoid that signal part. And by doing this, then another opportunity is we can treat whether that thread is, the other thread is on your same machine or on another machine. You don't care. You just put the request, say, I want this data, and into a IO queue. And after a while, the data comes back. So from that shard perspective, it's exactly the same. That's how we actually, what I mentioned about we treat the entire data center as a computer. It's essentially what I meant there. Yeah.
So again, it's like a decoupling, right? Because for compute and to keep the CPU as busy as possible, you just have one thread. And then for all the IO, you decouple that and put it in a queue, and the task is completed. And then when it's completed, it's marked as completed and so on. So that probably reduces the context switching and use the CPU as its full capacity, basically, right?
Yes. By the way, I have to say that we are not the first one to use this model. Of course, famous examples include ScyllaDB and DragonflyDB. So we are not claiming the credit here, but of course, there are probably a lot of other works before this doing this kind of similar approaches.
Absolutely. Yeah, we have had this episode with ScyllaDB and we discussed thread per core architecture, and it's really powerful. That sounds good. I wanted to understand a bit more about the fault tolerance part, right? Let's say I ingest my data, and let's say I have my multi-region deployment, or let's say a deployment even in the single region, but I need to have some sort of replication so my data is not lost. How is that handled? Because in a traditional, let's say MySQL or single node setup, you have to have the primary and then you have replicas, you have to set up the replication in between and so on. How does that work when it comes to EloqData? Does as a user, I have to care about it? Do I know about it? How does that work?
Yeah, that's also a very good question. I think that's basically touches up essentially to how actually EloqData is different from the other databases. So in our case, we also do all those things. So for example, data is getting replicated. We can use different ways of doing replication. The nice thing about us is because of decoupling, some of the replication we can actually offload to other services. For example, S3 actually does its own replication. So in that case, we don't care. We just assume that S3 is a persistent, it's never gonna get lost, right? But if we are not on S3, we are on on-prem deployment, then we can do the replication ourselves. What we can do is using any replication algorithms, like for example, using Raft, right? Also, so the primary, secondary way of doing replication, I actually worked on one of the earliest project called Pacifica algorithm, trying to do a primary, secondary replication. That algorithm was adopted in many of the following up works like Kafka, Elasticsearch. So my background was from the distributed systems. So I know that how to get from a distributed systems point of view, how can you tolerate failure? So when we were working on Pacifica project, that's like in 2006. And that was, at that time, people are not really familiar with how to tolerate failures. Paxos and Raft actually, Raft was not invented at that time, I believe, but I'm not sure about that. But anyway, at that time, very few people was familiar with how you deal with failures. So I was lucky enough to work at Silicon Valley Lab, Microsoft Research. I was a researcher there in Silicon Valley Lab. At that time, people like Leslie Lamport and many of the luminaries in distributed systems work in the same lab. So I learned a lot from them. So basically what we know is how to handle failures in a distributed system. We can keep the state, we can maintain the state and not getting lost. But there's another tricky part is you need to handle failures in the database sense. So database also has a lot of state, which is not persisted, not in the storage part. You need to do, we all know that we have database needs to have write-ahead log to recover transactions and so on and so forth. Those things are actually orthogonal. So what we actually did in EloqData is combine these two types of failures. You either lose part of the data state. What can you recover? You use replication. But you may lose your transaction context. What are you going to do? You use write-ahead log. So those things are actually not the same. It's actually pretty tricky. I think one of the, just anecdote. So I feel that a lot of the that the terminologies and also these two communities, distributed database community and also the database community, they traditionally don't work that well together, I would say. So there's always a little bit conflict. I was from the distributed systems community. At that time, when big table and all those kind of things were happening, people have a lot of argument, right? Max Stonebreaker originally wrote a lot of articles about why database have done a lot of things Google was doing before and whatever. But that's essentially the argument at the time. So from my understanding was these two communities, a lot of the terminologies. So what is consistency, for example? What is failure? And how would you maintain the state? What's the state? And all those kind of things are mixed together. And what is a write-ahead log? In the distributed systems, in Paxos, you need a log. You need to write a log. Database, you also need a redo log. What's the difference? How can they be combined? What's the tricky part? That's actually need to be figured out by both of by people familiar with both of these things. So that's actually one of the advantage of what EloqData. We are actually started by a few researchers and the industrial veterans. We have a couple of people also very familiar with database. They are from the database background. And I was from the systems background. We combine all these knowledges, trying to pick the best from both communities and trying to combine it into a single solution that works well in a data center. A database works well in a data center.
That's an interesting insight. Thanks for sharing.
Yeah.
Cool. The other thing which is very typical in database setup is that when I have my data, I want to have some sort of change data capture so I can connect my data and change events to some other system and power, I don't know, maybe analytics or some other use case. How does that work when it comes to EloqData? Is it the same integration, the connectors available, probably, I don't know, using Debezium or something?
Yes, that's also a very good question. So currently, from the ingesting part, we are using as I mentioned, we just use the regular APIs. So from the export part, the ETL part, currently we have our own CDC tools for different kind of data models. So we are actually trying to work on the surrounding tool sets. Still, I have to admit that it's still a little bit, because we are still a small startup, it takes some time to get the peripherals, I would say, into place. But most of the things are reasonably easy to do because we can easily connect. For example, we have a write-ahead log. We can connect that thing into a CDC, and then we can pull the data out. And so those kind of things are in the works. And I think also because we are an open source project, we welcome integrations from the other open source project. Yeah.
Okay, fair enough. When the Converge DB is out and generally available, do you see that the other databases like EloqKV and EloqDoc, EloqSQL, are they going to hide behind Converge DB, or there are specifically going to be some use cases that are specific to these databases? As a user, if I think about it, why can't I just use one database, which is, let's say, Converged database, and it gives me the freedom of using any type of data model I want, versus having to deal with separate databases like EloqKV, EloqDoc, and so on?
Yeah, that's also another very good question. So this actually, we have a lot of discussion in our team, inside our team also. So the idea was, so basically these four products are actually targeted different kind of users. For example, like MySQL and Mongo. So why people want to switch to these APIs? The reason was mostly because of better performance, better scalability, lower cost. That's usually the pain point felt by large corporations. If you are a large Mongo user or a Redis user, you are not happy with the performance or the scalability or the durability, whatever, and then you want to switch to a new database. That's you might consider using EloqData. The other database, the Converge database, might be targeting a different kind of users. So the user would be, they don't have any database maintainers, or they want to simplify their architecture. Or if they are a startup, I don't have five people to manage my databases, and I have to store all this data, which we can talk a little bit later about why AI is actually changing this. But basically, the idea was this is probably some people start from scratch. And in that case, you don't need to care about compatibility. You don't need to, not that much, right? So you don't care about compatibility that much. You don't care about which version of MySQL API does it support, and so on and so forth. So we'll just provide you some kind of SQL. It probably works enough. So that's why we feel that at least in the short term, we still need to support both types of systems, because for the individual products, we probably need to support all the surrounding tools, all the performance optimizations, also the different API versions, so on and so forth. That's the large industry care about. And for the smaller ones, we want to support it as for the converged ones, we want to support how to make it very easy to use. How can you build an MCP server? How to deploy it with one click? How the serverless version actually works seamlessly with your application, and so on and so forth. We also try to make it have a scale to zero capability, in the sense that a lot of the small businesses, they don't want to have their database open every day, right? So maybe during the evening times, you want to shut it down to save costs, so on and so forth. That's actually a different kind of feature request. But fundamentally, the technology-wise, a lot of these things can be reused they can cross over. And actually, that's a huge advantage. So from the external side, you can look at us and feel this small startup actually has 5 databases offerings, right? So it's nobody can do this if you think about it in the traditional way. Even a lot of database companies, they just maintain a single database and they need 500 people to work on it to make it up to date. And we are actually supporting so many. But from our point of view, it's actually the same, because the underlying storage and underlying transaction, everything is the same. And the computational part was already battle tested, as you mentioned. So yeah, that's very easy for us. Yeah. And also it simplifies the user.
Again, the power of loose coupling and abstraction that helps you reuse a lot. Perfect. You mentioned another interesting thing, and I wanted to ask you as a last thing. You mentioned that in this world of AI where it's like using AI agents every day in different workflows, right from coding to planning or travel plans or something, some analysis, or it's just everywhere. You're using agents of all types. I can imagine how is that going to change the way we use databases, or rather agents use databases. But I want your insights on how the idea of multimodal support and this idea of having one interface for different types of query patterns is powerful, especially in the AI age.
Yeah. That's also a very good question, and it's actually also very passionate for me. So basically trying to talk a little bit about this trend I foresee. Not I foresee, but I feel that it's actually a very important trend. It's essentially, if you think about it, I experienced the explosion of internet age. So from when people talk about database in 2000, before 2000, it's Oracle, right? So it's a single node database. And then in the last 20 years, there's a huge explosion. And there's so many choices out there. The reason was because database, nobody actually cares about database. They care about applications. So database is used to support applications. Why there is an explosion of databases is because we need to support the scalability, the scale, and everything, right? All the different data models needed to support internet age applications. Now we are actually at the very mature stage of internet. And now if you think about it, the agentic applications is going to become the main users of data or using the databases. So we feel that this is going to have a huge impact on the data infrastructure side. So for example, when I buy stuff on Amazon, and how much stuff do I buy? I probably made 1,000 purchases in the last 10 years. Now I'm actually also using ChatGPT. I look at my chat history. I probably chat 10 times with the ChatGPT agent every day. And I easily, 2 or 3 months, I got like 1,000 data stored in their database. And it's a lot of data because every chat takes like a 10K, probably even more, the tokens generated. So they actually have to store this. So this is basically means going forward, when the AI becomes the fabric of power in the next generation of increased application usage, we will have a lot of data. And also we will have a lot of query volume, because if I buy a t-shirt from Amazon, I click a link probably once every 30 seconds or something like that, right? But if I ask an agent to buy a t-shirt for me, it's probably just scan 1,000 t-shirts from different kind of vendors, trying to see which one is best that fit my description, fit my price range. This will create a huge amount of traffic going forward very quickly. That's what my feeling is. Now let's take a look at so that's why first let's summarize. So basically that's why we need a scalable or high performance databases. Then the question is, why do we need multimodal? The idea was before the agentic application at the internet age, the data is actually an exhaust. Essentially means you build an application and then the application, you can determine what kind of data to generate. So you have users, you have more products that you need to keep your database increasing, right? And then you write more data, you record more of the purchases. So the data is controlled by yourself. So you can determine what kind of, how much you want to keep, how much you want to, what type of data you want to store. But in the agentic application age, in the AI age, data is actually the fuel. So everyone can buy coding. So what's the difference between my application and the other people's application? Well, it's my mode. The mode is actually the data, the private data, and also the extensive data I can collect to support my application. Let's assume, for example, if you want to build a stock recommendation kind of application, then you probably want to store all kinds of account information and so on and so forth. Those are in the table format. It needs to be stored in a SQL database. And then you will probably also want to store a lot of the documents, like companies report, annual report, quarterly report, analyst report, all the kind of articles about that company, right? So those data is text. You want to create vectors, for example, to make it retrievable. And also you want to have a graph data to keep your knowledge base, like you have a lot of specific knowledges represented as a knowledge base. And then you want to store it in the queryable format. Usually that's a graph database. And so on and so forth. You probably also have streaming, right? The information is coming in, or the social media messages coming in. You have to have a streaming database. And you want to keep the chat history, which is generally a key value database. So on and so forth. You have to keep a lot of the data. And generally the company is a small startup. They don't have the resource to maintain like 5 or 7 databases out there. That's why you really need a multimodal database. And also, if your agent is talking with all these data sources, they want to have a consistent view, right? So you don't want to make one agent see a view and then another agent see a different view. So if a company is, for example, A company bought B company. So if one of the agents says, let's buy B company's stock, and another agent, the risk control agent, will say, I didn't see anything. I read my cash was still stale, right? So I didn't see anything. You shouldn't buy. And how to handle those kind of things. So this is the reason you really need a multimodal database to handle all your data. And also, it's very important that this database can scale, because when you start up, you have a small team, small number of small amount of data, but you could expand very quickly. After a while, your stock become picked up by some news media and everyone come to your site to explode growth. How can you handle that? You shouldn't expect like internet age of kind of slow growth. It can happen overnight. And then your infrastructure need to be scaled very quickly. So this is actually something I feel that going forward, all the companies needs to face this challenge. So yeah, I think that's why I think EloqData solution can be very valuable to solve this kind of challenge. Yeah, I have actually a kind of observation. So before, there is this trend, like in the last 5 years or so, I don't know, you probably also see this trend. Everyone was saying that scalability is actually not important. PostgreSQL is the universal tool. You solve it because whatever the workload you throw at it seems to be handling pretty well. And also now in the last 1 or 2 years, DuckDB. DB is also pretty popular, single node analytics solution. It seems to be handling all the workload very well. Why do you need the ClickHouse or Snowflake's distributed processing? So this is actually a huge question, and I think need to be answered or to be addressed by the database community, because I was starting my career in 2003, and the scalability is the word used for the systems research. And nowadays you are telling me that scalability is not important, which is very discouraging. So I actually have a kind of observation on this side, in the sense that, so what's the difference between 20 years ago and now? So 20 years ago, why people need to scale? Is because previously the database was trying to handle the workload of a single organization, a company, or maybe at most a bank's customers, right? So it's really limited. And at that time, so the database is handling that pretty well. The Oracle is pretty good. And then internet happened. At the beginning, people try to use all those infrastructure to handle the data need until they come. The reason was because the user exploded by several orders of magnitude, right? At that time, you are not trying to handle a single organization. You are trying to handle the entire web users, or we call netizens or whatever, right? That's millions, tens of millions of people instead of 20,000 people. Okay, at that time, Google is the first one, not necessarily the first one, but Google was one of the earliest ones to figure out this is not going to be sustainable. So they build all the distributed infrastructures. But if you look at the thing is that over the 20 years, of course, web users is growing, but it's not growing exponentially. In the last maybe 20 years, the usage growth, but the hardware growth even better, right? Even faster. Now, if you look at the Google paper, they were talking about 1 gigabyte of memory and maybe 2 cores in a single node. So that then, of course, you can't handle that kind of volume, like tens of millions of people. But now we have, if you go to Amazon, you have 32 terabytes of memory, storage memory. Actually, you can buy 32 terabytes, tens of thousand size increase. And also you can buy machines with 1,000 V cores or something. Now it's like 1,000 times faster. And if you look at the Google's paper, they deployed a 1,000 node cluster, right? So now you can handle it with a single node. So why do you need scalability? And the DuckDB case, it's a little bit later. Why is that? The reason was because the analytics workload, you are not trying to handle the concurrent users. You're trying to handle the historical data, right? So the historical data is aggregated over the years. So in the last 20 years, we probably aggregated a lot more data than the concurrent user. So that's why Snowflake and Databricks was pretty useful to handle this kind of large scale data. But now hardware caught up and your data is not increasing by that much. DB is okay, it's very useful. A terabyte data, it can handle reasonably well. But what I'm trying to say is that going forward, when the agent is going to use your applications, when your service is trying to face the future challenges, you're trying to face the future growth, these things will become very important. Because like I have a recipe, so suppose I'm a small website builder, I build a recipe, this website, right? So you know how many people are going to search for recipes? Well, it's probably not many, right? Also, when they come to my site, they will click one chicken noodle, they click one, and then, oh, this one is not good, try another one, maybe 1 minute later. And now suppose going forward 5 years later, we have robots. You know, everyone is saying that Thanksgiving, let's cook turkey. And we need the turkey. And 1 million of the robots will go, what are they going to do? They are going to come to the recipe website and trying to get all the turkey recipes, which will be like 5,000 of them. And then everyone will get this and they will issue this query to thousands of recipe websites. This is what kind of data will come in, the requests will come in. And that's why we really need to prepare for this kind of workload. The database infra and all the data infrastructure, data storage, they all need to be prepared. Yeah,
absolutely. I think that's a great summary. And I totally agree that this is only going to grow, right? And at a massive speed. And the growth of usage of internet and the applications done by human is nowhere comparable. So yeah, I can totally imagine why consistency, scalability, fault tolerance, and all of the amazing buzzwords that are important for databases and distributed systems are going to be even more important. And we need some solutions that can sustain that kind of load and that kind of guarantees. I can go on and ask you a lot of other questions, but in the interest of time, I think let's wrap up here. I'm really, thanks for sharing all the insights. Thanks for sharing all the internals of EloqData. And I'm sure that our viewers are going to like it. I'm also interested in learning more about the white paper whenever it is out. So do share it with me. And for our viewers, if you like this episode, please don't forget to hit the like button. And if you want to try out EloqData, you need more information, I'm going to attach all the details in the description of this video so you can take a look. And I hope you enjoy this episode. So thanks a lot.
Thank you.